So, welcome back. This is class 15. We talk about right triangle trigonometry and periodic functions. Today, project number 4 is collected, so hopefully that's done already. Project 5 is officially assigned. It will be due in roughly 1 week. You can take a look for a date next to this 18 right here. I just want to point out that we are about to start our study of trigonometry, and I hope you enjoy it because trigonometry takes up more than 50% of the course, the entire course. So I just want to point out here that trig goes all the way through the second test. And then even beyond the second test, this is more trig. Here, polar coordinates and complex numbers and vectors and parametric. They don't have the word trig in them, but it's a lot of trig. And eventually you get down to finally, after the third test is when we do our last little bit, and it's not technically trig. So for almost the entire rest of the semester, we're going to be talking about trigonometry. So buckle up. Number 1, lots to do today as we begin our study of a super important area of mathematics known as trigonometry. We start with a quick review of some basics about triangles. The sum of the measures of the 3 angles of any triangle is blank degrees. So hopefully we know this is 180. Draw a 90-degree angle, a 180-degree angle, and a 360-degree angle. Pause the video and come back when you've done that. Okay, so the first one I've got written in here is a 90-degree angle. It's called a right angle. Next one is 180. It's half of a revolution. It's also called a straight angle. And then how do you draw 360? Because 360 is essentially not doing anything. You'll land right back on yourself. So what you could do is just draw the one little line segment that I have, and then this little arc thing that will say, okay, we went all the way around, even though it looks like we didn't go anywhere. We will use Greek letters to stand for angles, most often using theta, which is written there in the parentheses. Number 2, 2 triangles are similar if the corresponding angles are blank and if the corresponding sides are blank. Okay, so the first blank says that corresponding angles are equal. And then the second blank says the corresponding sides are we could say they're in proportion. Or we could say, I guess that's fine, they're proportional. It's always the same multiplier from the sides of one triangle to the sides of a similar triangle. Number 3, let's look at a right triangle from the vantage point of an angle theta. The 2 legs can be called the adjacent side and the opposite side, and the long side is the hypotenuse. Let's label the sides of the smaller triangle below. Okay, so first one I'm going to label is the hypotenuse. It is the longer side. It's always very far away from the right angle. You can see this is our symbol right here for right angle. So this one out here is the hypotenuse. It's the longest side of a right triangle. And then the other sides are opposite and adjacent. Let's see, well, adjacent means next to, and the theta, the angle we're thinking about, is here. So the sides that are next to it are this one and this one, but one of them has already got a name, it's the hypotenuse. So adjacent must be this one over here. And that leaves only the word opposite, so we'll fill it in on this vertical side here, but hopefully that kind of makes sense that we call it opposite because it's so far away from the angle itself. So the opposite side is the one that's way over there. If the angle that I had been thinking about was up here, maybe this is the angle phi, then the word opposite doesn't apply to this side. Opposite would actually be that one down there, and this one over here would be the adjacent side. So what you call opposite and adjacent is really a matter of perspective. Make sure you know which angle you are focused on. Number 4, what can we say about the 2 right triangles above? Well, let's see. They're both right triangles. We got that. They both have an angle theta, which means that this remaining angle here, I don't know what it is, but they have to be the same as each other because you have only 180 degrees to play with in the entire triangle, right? And 90 and theta are accounted for in both. So what's left over has to be the same. These 2 angles here have to be the same. And in a triangle, and only in a triangle, that means that automatically the sides are in proportion. So for example, if I told you that the sides here were 3 and 4 and 5, just making up some numbers, 3 inches, 4 inches, and 5 inches. And then I told you that this vertical side over here was 12. then the fact that these triangles are similar means that the sides must be in the same proportion. So since this side to this side is a 12 over 3 or a 4, what that means is that every side of the bigger triangle is 4 times as big as the corresponding side of the smaller triangle. So that means that the bottom side is 4 times 4 that's already there, 16, and the hypotenuse is 4 times the 5, 20. So that's what we mean by saying in proportion, meaning it's the same ratio every time. In this case, the ratio is 4 to 1. Number 5, since any two right triangles with theta as an angle are similar, the ratios opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent are always the same. So for example, if we decided for some reason to calculate the opposite over the adjacent for the small triangle, all right, so what's the opposite side in that small triangle? It's 3, and the adjacent side is 4, compared to opposite over adjacent in the big triangle. So the opposite side in the big triangle is 12, and the adjacent side is 16, but if you reduce that, you get 3 over 4. And this has to happen in similar triangles. It's got to be the same ratio no matter how big the triangle itself is. In this case, if we just divide each of these numbers by 4, which was our little ratio here, then we get exactly the same reduced fraction at the end. Okay, so we give these ratios written as functions of theta names. So we are about to define 3 very important functions: opposite over hypotenuse, adjacent over hypotenuse, and opposite over adjacent. So here are their names. If you are looking at opposite over hypotenuse, we call that the sine of theta. Sine is spelled S-I-N-E, but we abbreviated S-I-N. I know it's not much of an abbreviation, but sine of theta. So it's a function of theta, and it is whatever you get when you take the opposite and divide it by the hypotenuse. If instead you look at the adjacent divided by the hypotenuse, we call that the cosine of theta, and we abbreviate that COS. And then finally, the ratio that we did up here, which was opposite over adjacent, you can see it there. That is called the tangent of theta, which we abbreviate TAN of theta. Okay, those 3 functions right there are called the trigonometric functions, or the trig functions. And they are super, super, super important for us. So sine and cosine, tangent are the 3 trig functions. Trig means triangle. They come very naturally out of triangles. That's why we call them the trig or trigonometric functions. There are actually 6 trig functions altogether. We are looking at 3 of them right now. We will see the other 3 in a future class, but we'll focus on these 3 for a while. Number 6. For the right triangle pictured below, let's find the 3 trig functions of the angle theta. Okay, good notation here. Sine of theta. You don't need the parentheses, but I'm putting it in there just to really highlight the fact that it's a function. Cosine of theta, tangent of theta. Okay, these are going to be numeric ratios. That's what we're after. Okay, with respect to this angle theta, let's label these things here as opposite, adjacent, and hypotenuse. Okay, the hypotenuse is this big one here. That's the 13. The 12 must be the adjacent. It's right next to the theta. And then the 5, therefore, is the opposite, the one far away from the theta. So if we do sine, looking up above at the top left, it says it's opposite over hypotenuse. Opposite is 5, hypotenuse is 13. We're done. Sine of theta is 5/13. Pause the video, see if you can fill in the other 2, and then come back. Okay, so hopefully we got cosine of theta is 12/13, and tangent of theta is 5/12. Next page. Now let's find the lengths of the sides of the triangle below. Assuming the adjacent side is 10 inches, make sure your calculator is in degree mode. Okay, it says the adjacent side is 10, so we'll put 10 there. And we're trying to find the lengths of the other sides of the triangle. And this is kind of a strange problem because it seems like we're given hardly any information. Okay, we have a right triangle, super, and the angle is 25 degrees, okay, and the one side is 10. but somehow that's supposed to give us the ability to find the length of the opposite side and the length of the hypotenuse. So here's how we do it. So let's suppose that we wanted to find the opposite side right here. So you know the adjacent side, you want the opposite side. Go back and look on the previous page and pick the one of those three trig functions that relates the opposite side and the adjacent side. Is it sine, cosine, or tangent? Hopefully you got tangent. So we know that tangent of theta is the opposite over the adjacent. At the end of this video, I'll give you an easy way to remember which one is sine, which one is cosine, and which one is tangent. But we know that tangent of theta is opposite over adjacent. And we know that the angle in this case is 25 degrees. So we're just going to put 25 instead of theta. The opposite side I don't know, I'll just leave it there. But the adjacent side is 10. Okay, so here's the deal. Tangent of 25 degrees is a number. I don't know what it is. But somebody has done some research and figured out to a very high degree of accuracy what tangent of 25 degrees is. And it's reasonable that that's something that's possible, because we know that if you're in a right triangle and one of the sides is 25 degrees, then the ratio of opposite to adjacent has to be the same. Doesn't matter how big or small this triangle is. It's similar to every other right triangle with a 25-degree angle in it. So somebody spent a lot of time trying to figure out with a high degree of accuracy what that magical ratio is. If this is to scale, which I don't promise it is, then maybe this opposite side is like a third of this adjacent side. So I wouldn't be so surprised if tangent of 25 was around 0.3. But the fact is, it is known what tangent of 25 is. And so I just want to point out that we can use our calculator to essentially just look up what the tangent of 25 is. It might seem like magic in the beginning, but it's really not. It's just looking up something that has been studied and discovered to a great degree of accuracy. This whole degree mode business, if you have a TI 83 or 84, hit the mode button, scroll down to this thing that says radian and degree. We'll spend a lot of time talking about radians, but for right now we're in degrees, so make sure that that is highlighted, not this one. We'll quit out of here. We'll type tangent of 25. Again, if it's to scale, I won't be surprised if it's something like 0.3. Maybe that's about a third of this one. Okay, 0.46. I can buy it. Maybe this is a little bit less than half of that one. I was just estimating. But tangent of 25 is known, and we just look it up. So we're going to write that number here. And then in order to figure out what the opposite side is, we just solve by multiplying both sides by 10. So the opposite side is roughly 4.663. Okay, so now we'll do the same thing to find the hypotenuse. Okay, well, once you know that this side is about 4.66 and this side is 10, you can actually use the most famous theorem in all of math to find the length of this side. That's the Pythagorean theorem. But how about we don't do that? Or you can do it if you want to, but I want us to practice with this new trig idea. So how about you pick one of the other functions? Can you find the function that relates the hypotenuse and the adjacent side? Hypotenuse and adjacent. So that function is cosine. So we know, oops. We know that cosine of the 25-degree angle is equal to the adjacent divided by the hypotenuse. So cosine of 25 is, the adjacent is 10. Hypotenuse is the thing we're trying to find. Let's just accept that we're going to look up cosine of 25 in a minute. I don't want to put anything in now. I want to give you the way to get the most accurate answer your calculator can give. So instead, what I'm going to do is multiply both sides by hypotenuse. So we get hypotenuse times cosine of 25 is 10, and then divide both sides by cosine of 25. After all, it's just a number. And so this is the most accurate answer that we can get. 10 divided by cosine of 25. So you've got your three trig buttons right here. There's sine, cosine, and tangent. I said there are 6 trig functions. We'll talk about how to get the other ones on the calculator soon enough. So we said 10 divided by tangent of 25, and we get 11.034. Okay, so that's our answer. If you want, you can check with the Pythagorean theorem. If you know 4.663 and 10, try the Pythagorean theorem. Hopefully we get something very close to that. Number 8, for most angles, the trig functions are ugly numbers, but there are a few special angles for which we should memorize the exact value of the trig functions: 30 degrees, 45 degrees, and 60 degrees. Here are two special triangles whose sides we'll label. We'll use them to fill in the table below, memorize the triangles, or memorize the table and memorize them soon. So here are two special right triangles, the 45, 45, 90, and the 30, 60, 90. And we're going to label the sides. So these are some numbers that I have memorized. The 45, 45, 90 triangle has sides 1 and 1, and the hypotenuse is square root of 2. I don't know what to tell you in terms of memorizing it, but it's something that I've memorized. And so if we wanted to use that triangle to find, for example, the sine of 45, well, that just means do the opposite over the hypotenuse. Doesn't matter which 45 you pick, I'll pick this one here. Opposite is 1, hypotenuse is root 2, so this thing is just 1 over root 2. If I want to do cosine of 45 and put it in here, well, that's just adjacent divided by hypotenuse. Again, I'll pick that 45-degree angle. Adjacent is 1, hypotenuse is root 2, so this ratio is actually exactly the same. This is also 1 over root 2. And then finally, tangent of 45 down here, it's the opposite divided by the adjacent. Opposite is 1, adjacent is also 1. 1 divided by 1 is 1. Okay, so there's some facts about the 45-degree trig functions. And then we'll come over here into the other triangle. And again, I will say I have memorized some numbers. I know that opposite the 30 is a 1, hypotenuse is 2, opposite the 60 is root 3. In terms of memorizing it, it's 1, 2, almost 1, 2, 3. It's 1, 2, root 3. But you do have to know which one goes where. Okay, given that, I'll fill in one of these and ask you guys to fill in the rest of them in a moment. Let's suppose we want the sine of 30. So again, sine is opposite over hypotenuse. Here's the angle we're focused on. The opposite side is 1, hypotenuse is 2, so 1/2 is the answer here. So pause the video and see if you can fill in the other 5 blank spaces. Come back when you're done. Okay, so maybe pause the video again and make sure that your answers agree with my answers. Hopefully my answers are right, yours too. Okay, and there are a lot of numbers in this table, and I'm going to ask you to just learn them. But I want to give you one little hint in terms of memorizing. I'm going to write some of these numbers for sine and cosine in a funny way. Sine of 30 degrees is a half. I'm going to write that strangely as the square root of 1 over 2. And it's the same, right? Because the square root of 1 is just 1. And then in the middle one here, I'm going to rationalize, which means multiplying top and bottom by root 2. So you can check, I'll actually do this in red, but you can check that this is really the square root of 2 over 2. And so now I'm just going to point out a pattern, the way that we've written this, these numbers in this kind of funny way. That's the square root of 1 over 2. That's the square root of 2 over 2. That's the square root of 3 over 2. There's a nice pattern there. Square root of 1 over 2, square root of 2 over 2, square root of 3 over 2. And the pattern works exactly the same here. That's root 3 over 2. That's root 2 over 2. That's root 1 over 2. So the sine goes up, 1, 2, 3. Cosine goes down, 3, 2, 1. Okay, you don't need to think of it that way, but I just wanted to point out the pattern in case that makes it easier for you to memorize what's in the table. Number 9. We can use the trig functions to find all kinds of things that would be hard to measure directly. Suppose I walk 100 feet away from the east building and I use a protractor to determine that the angle of inclination from my eyes to the top of the building is 38 degrees. Okay, so let's draw right here. So we've got the east building, not to scale, and then I walk 100 feet away, and then my eyes are someplace up here off the ground a little bit. I'll draw horizontal, and then I'll draw up to the top of the building, and it says the angle of inclination is 38 degrees. So that's this angle in here. To the nearest tenth of a foot, find the height of the building. Assume my eyes are 5.5 feet off the ground. So that means this distance in here is 5.5. Okay, so first thing to observe is that this dotted horizontal line is also 100. That's how far we are from the building. So basically you've got this triangle that's most of the building, then 100 feet, and then a 38-degree angle. And we've already discovered that as long as you have that right angle there, we can use this trigonometry stuff to find the length of the side. So first of all, what's the name of that side? Is it adjacent, opposite, or hypotenuse? With respect to that 38-degree angle, that's the opposite. How about this 100? That's the adjacent. Which of the three trig functions relates the opposite and the adjacent? It's tangent. So we know the tangent of 38 degrees is opposite over adjacent, which is opposite over 100. So tan 38 we'll type in a moment, but first solve for the opposite side by multiplying both sides by 100. So we go 100 tan 38, which we can type in on the calculator. And we get 78 point, let's see, we're going to the nearest tenth. So, yeah, nearest tenth, so 78.1 feet. So that's this length right here, 78.1. So then to find the height of the building, we just have to add the 5.5 feet that my eyes were raised off the ground. So then the height is roughly the 78.1 plus 5.5 feet. So about 83.6 feet. And this might not be the most interesting problem you've ever tackled, but I contend that it's a pretty powerful tool that we just learned how to use. Measuring the height of that building directly, like with a tape measure or some other device, could be quite difficult. You have to get somebody up on the roof and be very careful. They don't want to fall. Maybe the tape measure isn't long enough. It's complicated. But walking 100 feet away from the building is really easy. And we can do that without ladders or danger to ourselves. And then taking a protractor, or engineers have fancier tools than that, to estimate an angle of inclination is also easy. So the point is we just measured something without actually ever touching it, without being anywhere near it. We measured something that was easy, 100, 38 degrees was also 100. We used the power of the trig function in order to measure something that might be hard. We'll see more of these soon enough. Number 10, note that at the moment, our definitions of sine, cosine, and tan have a domain of, well, we know we have a right angle, and we know we have a theta, and we know we're in a triangle. And the biggest angle you could possibly have as another angle in a triangle would be 90, and we can't really have 90. And the smallest one would be 0, and you can't really have 0. So at the moment, sine, cosine, tangent are only defined for numbers between 0 and 90 because they come from a triangle. I will point out that if I typed in, for example, sine of 100, which is bigger than 90, the calculator doesn't have any problem with it. So somehow there's some other thing that we're going to need to talk about, but at the moment, these functions are only defined between 0 and 90 degrees. 11. There's a nice little mnemonic device you can use to remember these things, these three trig functions. So here's a made-up word, SOHCAHTOA. SOHCAHTOA is supposed to tell you that, for example, the sine function is the opposite over hypotenuse. And the next piece of it, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. It's a nifty little mnemonic device. However, it's useless if you can't spell the made-up word SOHCAHTOA, so somehow you got to get to a point where you know what those three functions represent. 12. There's a brief introduction to periodic functions from illuminations.nctm.org. It's a great site. Let's read through the vocabulary and fill in the blanks in the graph below. A function that repeats exactly the same pattern over and over again is said to be periodic. So for example, this graph right here looks like some capital M's with curves in between them is periodic because it repeats exactly the same pattern over and over again. The period is the shortest horizontal length that repeats. So to find the period, what you want to do is pick one point and then move over until you found the corresponding point on the next cycle. So the period is just that horizontal distance in there. Now there wasn't anything special about the point that I picked there. We could just as well have picked this point and then its partner. That horizontal distance is the same as the purple one. We could find another one. You could, for example, pick the point that hits right here on the x-axis on the curve, and we could find the next place that that happens. Maybe it's over here. And again, that green is the same as the purple and the other green. So how long is it? Well, you just have to count boxes or look at the x-axis. Looks like this one is a total of 6. Is that right? So here we go from 3 to 9, which is 6. Here we go from about 4.5 to 10.5, that's 6. Here we go from -4 to +2. Guess what? It's 6. Period is 6. It's a number. The midline is the horizontal line that goes through the vertical middle of the pattern. So in this problem, the midline is dotted. All right, so what I call the midline is what this picture calls the axis. It's this dotted line right here, and it's the thing that's halfway in the middle of this graph, vertically speaking. So how do you know what halfway is? Well, you look at the top. So the top would be like up here. It looks like that's at 4. So you look at the top, you look at the bottom, which is down there at -1. So really I'm looking at that distance between 4 and -1, which is a total of 5. So if I want to go half the distance and the total is 5, and I need to go 2.5 in. That is to say 2.5 down from the top or 2.5 up from the bottom. Either way, you land on that thing which we call the midline. So 2.5, let's see, this is a 4. And if you do 4 minus the 2.5, you get 1.5, which is exactly where this dotted line is. Or you could go to the bottom, which is at -1, and add the 2.5. Whether you go up or down, doesn't matter. You should get the same exact thing. So the axis is y equals 1.5. And I just want to highlight again, just like when we had equations of vertical asymptotes or horizontal asymptotes last class, here the axis or the midline is also an equation. So don't tell me the axis or midline is 1.5. Tell me it's y equals 1.5. Okay, and then the amplitude is the maximum vertical distance from the midline. We've actually already found it. How far is it between the midline and the bottom? So there's the bottom. So that total distance is 2.5. Same thing from the middle up to the top. It's also 2.5. So the amplitude is 2.5. Okay, and then finally down below, we've got this Ferris wheel problem. Consider the Ferris wheel pictured below. Its diameter is, okay, we're going to make a slight change here. It says 24 meters, but I'd like to change that to 20 meters. Doesn't matter today, but it's going to make it easier to do something next class. So diameter is 20 meters. It's rotating at 3 revolutions per minute, and at its lowest point, it is 5 meters above the ground. That's pretty high. Assume the ride starts in the pictured position. That is right out here. That's at t equals 0. Let's make a sketch of the graph that models the height of the rider in meters as a function of time after the ride begins in seconds. Okay, so we'll make our graph. Time is down there in seconds. Height is up here in meters. Where is this thing initially? How high is it off the ground? Well, let's see. It's 5 meters down there at the bottom, but then this distance in here is a radius. It's half of the 20, which was the diameter. So that's a 10, and also up here is another 10. So there's your 20. So how high is it in the beginning? Well, in the beginning, it's this high off the ground, which is 5 plus 10 or 15. So in the beginning, we are 15 off the ground. Maybe we'll mark this thing in 5s. And so in the beginning, we're 5 meters off the ground, and that's a dot right there at t equals 0. And then at some point, we rotate around and we make our way up to the top. So how high are we at the top? Well, at the top, we're this distance plus 5 more. So that's a total of 25. So at some point, we're up there at the top at 25. Probably this is a good time to figure out how long it takes to get there. So if you are going 3 revolutions per minute, that means 1 revolution for every 20 seconds. And 1 revolution is going to take us all the way back around. But what I want to know is how long does it take to get there? Well, that's clearly a quarter of the revolution, right? We got these 3 different quarters going around here. So if you take your 20 and you divide it into fourths, then you can figure out that a quarter of a revolution takes you 5 seconds. 20 divided by 4. So how about we go ahead and label the horizontal axis here in terms of 5s as well. 5 seconds, 10 seconds, 15, 20. We'll do 25 and 30, that's enough. So I guess what we're saying here is that it'll take us 5 seconds to get up to the top, and when we're at the top, we decided we were 25 meters off the ground. And then another 5 seconds, so 10 seconds altogether, we land here, so we are this far off the ground, which is 15 again. So after 5 more seconds, we're at 15. 5 seconds after that, we're down at the bottom, which is only 5 meters off the ground. So that's down here. And then 5 seconds after that, we're right back to where we started, which is again 15 meters off the ground. That's here. And then it repeats. It goes up to the top, then back to the middle, then back down, and back to the middle. And so if you make your best guess for the graph of this thing, I mean, I suppose you could just try to connect with straight lines. That wouldn't feel very good if you were riding on the Ferris wheel, because there would be a very abrupt change in your velocity right there at the top. So how about instead we try to make this a little bit smoother, something like this, and then it repeats. 14. For the Ferris wheel, identify the period, midline, and amplitude. Okay, so period is the horizontal distance between two points that are corresponding. So it's tempting but wrong to say that these are corresponding points, because this guy, well, initially you're on the way up, and then you hit the next point on the way down. They're not the same. So if you really want to find the point that's like this, you got to find the next time when you're on your way up. So you could say that these are corresponding points. Might be safer just to pick something at the top or bottom. So for example, how long does that take? Well, that's between 5 seconds and 25 seconds. Altogether is 20 seconds. Which makes sense because that was how long it took us to make 1 complete revolution, and then the whole process starts over again. The midline is y equals, or maybe h equals. So it's the middle. The middle is right here at 15. If you weren't sure how to, yeah, that's fine. Middle is at 15. So h equals 15 is the midline. And then finally, the amplitude is just how far it is up or down from the middle to the top or the middle to the bottom. Either way, it's a total of 10. So the amplitude is 10. Amplitude is always a positive number. So you wouldn't say negative 10. Okay, activity is on the next page. Do your best to try it before taking a look at the answer key, which follows, and you could also check out the video for this activity after you've had a shot at it.